So this video is designed to give you some basics about titration curves. We are going to spend some time in class together working on titration curves and visualizing what's happening and so on and so forth. But this is going to give you some baseline information. So in order to do a titration, remember that you always need to have some sort of indicator to let you know how things are changing. The indicators let you know the pH range that you are transitioning from H pluses to OH minuses in. Indicators are typically weak acids that will bond or unbond to the H pluses that are around. So here's an example, phenolphthalein, you used a lot first year. Notice what will happen is this hydrogen will get removed, it'll get pulled off and bond with water, and notice what happens to the bonding. It rearranges the double and single bonds, and as a result, you wind up with it interacting with the light differently, and so you wind up producing a new color. So it's not the fact that you've taken the H plus off, it's the fact that you've rearranged the bonding scheme here that allows for light interaction at a different wavelength. Methyl orange is another indicator that you've used. Notice again, we've got the double bond between the nitrogens here, but when we've added the H plus, now we've got a rearrangement and the double bond occurs here. So once again, that change in structure is what allows the electrons to interact with the light differently and produce a different color. Depending upon what your pH range transition is, you're going to want to pick a certain kind of indicator. Notice phenolphthalein, the common one that you're used to using, transitions just above pH 7, pH 8. So that's why we used it, because we were titrating a strong acid with a strong base. You'll see that in a couple evidence in a couple minutes. Just a reminder, when you do a titration, typically you have the unknown solution in the flask. In this case, usually the HCl. The sodium hydroxide is in the burette, so we add indicator to the HCl, start adding base. As the amount of base increases, that color transition happens with the indicator until at one point you've transitioned all of the molecules to that color and wound up with a colored solution. You can also follow the pH using a pH meter. We're going to do that. Basically what it does is it takes the electrolyte voltage, so the amount of ions that are in solution, takes that and translates that into a pH. So in a titration curve, there's a couple things you're going to see. It's always going to be pH versus volume. And so the pH will be on the y-axis, the volume is on the x-axis. And so as you add base, typically, you're going to see what happens to the pH. pH is going to go up slowly at first because there's a whole lot of acid there and not a lot of base. But once we start approaching that equal point, that equivalence point where the H plus and the OH minus equal each other, you're going to see a very big transition in pH, so you see a big vertical line. And then after the equivalence point, pH is going to change once again a little more slowly because all we're adding is H pluses. So here's an example of a titration curve with a strong acid, strong base. This is where we always start because it's the cleanest one to look at. So in terms of strength, remember that the HCl is going to be 100% dissociated. So all the H pluses are going to be available, which means your starting pH is going to be relatively low. And as you add base, it's going to change very sharply and very linearly because all that H plus is currently available. So any sodium hydroxide you add to it is going to create water, decreasing the number of H pluses. As you approach the equivalence point, notice that the pH changes much more quickly. And then when you hit that equivalence point, now you have a completely neutral solution. You have no extra H pluses or OH minuses. And so the pH of that equivalence point winds up being 7. And then very quickly, if you continue to add base, it jumps again to a much higher pH because we are adding more OH minuses and there's no H pluses around. So these are the things that you want to take a look at when you're looking at a titration curve for identifying things. Strong acids and bases are going to start very low and very high. The lines are going to be very, very straight when you have more of one of the ions than the other. This is going to look very different here if we have something that's weak. The equivalence point is going to be at pH 7, and as you approach that equivalence point, there is a big, long vertical transition. You very quickly jump from being acidic to being basic. That's going to look a little bit different, so take a mental picture of this. It's going to look a little bit different than the next slide. Here's what happens when you have a weak acid titrating with a strong base. So we still have sodium hydroxide. So notice that it's still pretty vertical up here. But take a look at what the bottom area looks like. Because we've got a weak acid, not all of the acid is dissociated. So we've got a lot of H pluses unavailable, which is why it starts out higher than a strong acid will. And you have this curvy area here because we've got to break apart that molecule in order to get those H pluses to react with OH minus. So you see a really a bigger jump here until we get all of that H plus dissociated. Notice also that the equivalence point is the line leading to the equivalence point is pretty darn small. There's very little vertical here. And also notice that the equivalence point is above 7. And that's because you have hydrolysis going on. We'll take a look at that in the next slide. But basically at the equivalence point, remember that you have the weak acid, or the weak base, acetate, will accept H pluses from water, so it'll react with water. You'll wind up making acetic acid, and you'll have excess OH minus left over. And so that's why the pH winds up being higher than neutral. So again, here's just a review of what we talked about. As the base is added to the acid, both the HA and the A minus exist. This means that to determine the pH, you've got to use an ice chart. You can't just see how much H plus you have. Other couple ideas that you got to remember at the equivalence point, this is where hydrolysis is going to happen. The anion of the salt is a really weak base and reacts with water to form the original acid. So the pH, you've got extra hydroxide in solution, and so the pH is going to be above 7 as opposed to neutral. There is a really nice example of going through different types of acids and bases at this U of I website. Your book has some good examples. We're going to do some examples. So in terms of calculations, we're actually going to do those together, which is why I don't have a whole lot of calculations here. Here's another visual with weak acids and strong bases. As the acid is weaker and weaker and weaker, it's going to start at a higher and higher pH. You're going to have a very weird jump here because we've got to break apart all of those acid molecules that are still whole. The equivalence point is going to be very hard to figure out in some cases. Look at this. There's hardly any equivalence point here. And it's very high because of how weak the acid is. So we're not going to work with anything this extreme. We're going to keep stuff so that you can see a vertical to a certain extent. And then if we switch gears a little bit, take a look what happens when we have a strong acid titrated with a weak base. One of the big things, so strong acid, it looks very similar to what the HCl titration curve looked like at the bottom. But one big thing is that the equivalence point is going to wind up below 7. That's because since you have a weak base, its cation is going to react with water to recreate that base and leave extra H pluses around. So you have hydrolysis, but in the reverse direction. So when you look at a titration curve, one of the really big tells is where that equivalence point is. If it's below 7, you have a strong acid with a weak base. If it's above 7, you have a weak acid with a strong base. And if it's at 7, you have 2 strong ones. If you are titrating 2 weak ones, it really depends on what the Ka and the Kb's are. So here is a strong acid with a weak base, but instead of titrating with base, we're titrating with acid. And so we're starting high and going low, but you see the same kind of change. Here's sodium hydroxide strong. You've got that nice straight line until you get close to the equivalence point. Here's ammonia being titrated with HCl. Again, notice that curvy starting point that you had, equal but opposite to what we saw with acetic acid. So those are some tells that you want to make sure you learn, because you could be presented with a pH curve, a titration curve, and the question might be what two solutions are being titrated. So you want to make sure you're comfortable with that. Titration curves for polyprotic acids look a little weird because you're losing more than one H+. So in the end, when you finally neutralize everything, you've got a couple of different equivalence points. So here we've got H3PO3 starting off. It's weak, so notice it's a curve. Rather than nice and straight. The first equivalence point is going to be pretty low because you don't have a whole lot of H+ being produced. There's still a whole lot of H attached to the molecule. So here's the first equivalence point where we transition from the loss of one hydrogen ion. Here's where we transition to the loss of a second hydrogen ion. And we don't have the third being shown because that third one comes off almost very difficultly. So it would take a whole lot more to get that reaction to happen. So they've just shown you the first two equivalence points. One of the things that makes titrations nice is using the Henderson-Hasselbalch equation. You can use this equation to find pH without having to go through a lot of the work that I'm going to show you guys in class. But we're running out of time, so I think I'm going to pause here and we'll pick up Henderson-Hasselbalch in the second video.